Sorry about that, and thank you for being here on a sunny Sunday afternoon. So today I'm going to talk about maximizing temporal clustering. Did you enjoy work with my PhD advisor at Carnegie Mellon University? So we are interested in human and animal behavior understanding, and the problem that motivates it work is to automatically build a taxonomy for behavior. For example, here we have the video of honeybees. Now the bees done to communicate the distance to the food source, and as you can see, they perform some behavior repeatedly. So what we want to do is to automatically build the taxonomy for those behaviors. So let me explain what I mean by that. So here, each segment here represents one bee dance, and it's in one multi-dimensional time series. And what we want to do is to segment it into non-overlapping segments such that together they form k different clusters. And each of the clusters correspond to some meaningful behavior class. For example, turn left, turn right, or waggle. So temporal segmentation and clustering is useful for a number of the other applications, for example, for human activity understanding and for like speaker diarization. There has been quite a number of related work in this area. So probably the most popular method would be chain point detection. Now chain point detection detects the position at which the statistic before and after the chain point differ. So they detect local boundary instead of building a global model for temporal event. Another popular set of technique is to use a variant of dynamic Bayesian networks such as hidden Markov model or switching linear dynamical system. Now, a lot of these methods here actually supervise learning. It means that in training we require the segmentation and label for the time series. Also, all of these techniques are generative model. They have a problem for generate the new class, which is the class of hue variation. Also, most of them are generative probabilistic model, which in learning and inference we have to normalize for the probability, so the learning and inference can be quite complicated and sometimes even intractable. There's another set of technique called subsequent time series clustering. Now subsequent time series clustering finds subsequences of time series that form tight cluster. So they don't invoke a coherent temporal segmentation model because the subsequences can overlap one another. Also, they tend to use k-mean, which is only optimal for spherical cluster. So what we propose in this paper is an unsupervised discriminative method for temporal clustering. So we invoke a coherent segmentation model and we build a global model for temporal events. Now let me remind you of what we want to do. Even a set of multi-dimensional time series, what we want is to find the chain points and the class label such that when we map to the feature space, points that belong to different classes can be separated. Furthermore, we want the classes to be well separated by a margin. Now, so the goal is to find a set of chain points and the class label, chain point S and class label Y, to maximize the separation between classes. So clearly we have to optimize for two things at the same time here. So it's a difficult problem. So let's first consider an easier problem. Now suppose someone gives us the chain point. What we want to do is to find the class label to maximize the separation between classes. What I mean by that is if we map it to the feature space, we want to cluster these points into different classes so that they can be separated by a margin. Now, so this problem is called the margin clustering, or MMC. So the formulation of MMC is very similar to support vector machine. So the only difference here is in learning, we have to optimize for the class label together with the weight vectors. If you look at the constraint down here, basically it says the dot product between the point and the weight vector is the cluster score for assigning this point to this cluster. So we want the score for the right cluster of Xi to be much bigger than the score for assigning Xi to any other cluster by a margin of 1 here. Okay, however, Furthermore, we can also allow the constraint to be violated and then by introduce slack variable and then penalize for the slackness. Now, however, MMC has a problem of cluster degeneration. Let me illustrate this point by comparing with k-means. Now, in the case of MMC, we maximize the separation. In the case of k-means, we actually maximize the compactness of the cluster. So, suppose we want to split a cluster into two subclusters. In the case of k-means, we end up with two new clusters and they are more compact. In the case of MMC, the new cluster needs to be separated. So, we have to spend extra effort to separating them. So, why k-mean prefer more cluster? MMC prefer fewer cluster. And this can lead to the problem of cluster degeneration. Okay, so people address the problem by introducing the cluster balancing constraint. For example, thou enforce the constraint on the average cluster score. So basically, he said, like, given any two clusters, the average cluster score should be similar. However, in practice, we found it doesn't work very well. One of the reasons is this constraint not even be translation invariant. If the data is centralized, then this constraint has no effect at all. So what we propose in this instead is we're going to enforce the constraint on the membership of the cluster instead of the constraint on the cluster score. So we're going to require a cluster to have some certain number of points. And in our experiment, we're going to set the L here is that 1/3 of the average number of points for each cluster. All right. So the bad news is MMC is not convex, but we can use block coordinate descent to optimize for it. For example, here in one iteration, the first step of one iteration, we can fix the weight vector and optimize with respect to the cluster label and the slack variables. And in the second step, we can fix the cluster label and optimize with respect to the weight vectors. And so, in our implementation, we use a multiple random initialization and we choose the one with the lowest energy. Okay, so far, what I described is given the segmentation, I described how we can build the segmentation model, or no, the clustering model, which means the weight vector W1, W2, and W3 here. Next, I'm going to talk about, given the clustering model, how we can come back and update the segmentation.
We assume that after the segmentation, the points are linearly separable. I mean, because in the picture it looks like a linearly separable, but in the segmentation you don't see it. It just change points.
Yes, very quickly. Yes. No, they don't have to be separable, so we can penalize for the slackness. Basically, yeah. Okay. Now, so the input for the task is given a clustering model, the weight vector, and a particular time series. What we want is to find a set of chain point and segment label such that each segment here can be confidently classified. What I mean by that is, let me denote the feature vector for this segment as the quantity here. What we want is the cluster score for this segment for the cluster YT must be much bigger than the cluster score for any other cluster. And again, we come back to the question, we can allow the constraint to be violated and then penalize for minimize the total violation. And also we can enforce that a subsegment has some maximum length. So this formulation can be optimized very efficiently using dynamic programming. So details are in the paper. Okay, so now what I'm going to describe is how I compute the feature vector for a segment. Now, our time series is a multi-dimensional time series. So each frame here corresponds to a feature vector. So what we first do is we can look at the quantization space of the frame level feature vector, and if it is associated with like the cluster U here, then we're going to have a binary indicator vector that indicates that, okay, this particular frame belong to this cluster or this idea. You can think it's like the observation model, like in hidden Markov model. So this vector can encode which state this frame belongs to. So we also encode the transition between consecutive frames. What I mean by that is to look at the previous frame, and if it belongs to state V, then we have a matrix that encodes this transition. We vectorize it and concatenate these two vectors, and it's going to be the feature vector for this particular frame. And the feature vector for the whole segment is the sum of the feature vector for the frame in the segment. So this is inspired by the backup word model and also the hidden Markov model. Okay, so in practice, we actually use the soft clustering, the soft assignment instead of the hard assignment here. Okay, so now let me explain the experiment. So there are two sets of experiment here. On the first set of experiment, we perform the clustering. We only perform the clustering experiment. There's no time series in the first set of experiment. So we compare different clustering models. On the second set of experiment, we perform joint segmentation and clustering. And for the performance measure, we use the purity measure and the pair counting measure. Now, purity measure is by far the most popular measure, but it's only applicable for when the number of clusters is equal to the number of classes. So to analyze the sensitivity analysis, we use the pair counting measure. Okay. Now, so to benchmark the clustering performance, what we perform on the UCI dataset. Now, this collection contains many datasets, but we filter out the ones that contain categorical or missing attribute, and also we want the set of dataset to contain diversified number of classes. So we didn't have many choice at the end. So, for example, the dataset here, digit 17 is the digit dataset with only 2 classes, and the number of classes are provided in the second column here. And as you can see that when the number of classes is small, all methods perform equally well. Now, when we increase the number of classes, in this case we have 10 classes, then the original formulation of MMCs has the problem of cluster degeneration. That's why it performs very poorly. This happened to other data sets as well. As the number of classes increase, the performance of the MMCs suffer a lot because of the cluster degeneration. Okay, now so the next experiment is for temporal segmentation and clustering. So this data set, we performed the experiment on the Weizmann data set. So this data set is the human action data set of 9 people and 10 action. And here is how we compute the feature vector at the frame level. So given the original video, we first do the background subtraction to get the binary mask. And we use the distance transform to get the soft mask of the binary mask. So here the result, okay. So on the x-axis here, I vary the number of classes. And on the y-axis here, I'm showing the accuracy, so the higher the better. So in this case, we assume that we know the correct number of classes. So we set the number of clusters equal to the number of classes. So the red curve here is the result of our method, and the blue one is exactly the same with our method, except we replaced MMC with k-means. So in this case, k-mean doesn't do very well. Okay, yeah. And then, so in the second experiment here, we perform the sensitivity analysis. So in this case, we suppose that we don't know the true number of clusters. So we're going to fix the number of classes equal 10, but then we vary the number of clusters. Now, because the number of clusters are different from the number of classes, we're going to use the pair counting measure for this experiment. Basically, the black curve here, we answer the question, now if 2 frames belong to different classes, are they belong to the same cluster or not? I'm sorry. If two frames belong to different classes, they should belong to different cluster. And on the blue curve here is the opposite. Basically, if two frames that belong to the same class, they should belong to the same cluster.
They belong to the same cluster, they should belong to the same class.
Or vice versa, right? The same cluster.
Because the number of clusters is different than the number of classes. It's only if they're in the same cluster, they're in the same class.
I think they are similar in some sense, yeah, but we can take it offline. Yeah, thank you. And the red curve here is the average of the two. And as you can see here, if you look at the average of these two curves, then they are quite stable even with different number of clusters. Okay, so the final experiment is on the Honeybee dataset. So this dataset contains 6 sequences, 3 actions. So the bees are visually tracked. Now, so here I'm showing the result for 3 methods on 6 sequences. The first one is either using switching linear dynamical system. The second method here is exactly the same with our method, except we replace MMC with k-means. So in this case, k-means do pretty well. It's even better than switching linear dynamical system. But it's still worse than our method here. We also compare the human labeling and the automatic segmentation. If you look at the 2 sequences carefully, you can see that the classes are correct. The error usually happen at the boundary of the segment. So this is a time series data. So human label might not even might contain error itself too. Okay. So in conclusion, so what we propose is an unsupervised discriminative method for jointly do temporal segmentation and clustering. And so we address the degeneration problem of original formulation of MMC and the criteria that we to maximize the margin between cluster. So we performed the experiment on the Honeybee dataset and the human action dataset, and we achieved state-of-the-art performance, and also we have the high agreement with human labels. For future work, like we want to have a method that can automatically select the number of cluster. And right now, and maybe a better initialization strategy for or convex relaxation for the formulation. Thank you.
Let me start the question.
Yeah.
So why did you choose maximum margin clustering? I mean, you could try the same task under different clustering objectives, and this is kind of uncommon objective, the maximum margin. So why did you choose this one and not any other more common clustering objective?
Yeah, for example, in say k-means, for example, then k-mean doesn't have a mechanism for feature selection, for example. Is one of the most common out there. Yeah.
What do you mean by a mechanism for feature?
So if you have a k-mean and if you have a feature vector with a lot of noisy feature in there, then it doesn't do very well. And it's only optimal for spherical cluster. And I think one of the nice things about the support vector machine or the max margin clustering is it allows you to select a feature weighting for each of the feature too.
Another question. So in that case, let's take a speaker again.